So, thank you very much for all that joined the fifth SEENET-MTP seminar, which will be given by Calin Lazaroiu from Department of Theoretical Physics, Institute of Nuclear Physics in Bucharest-Magurele. The title of the talk is Dynamical RG Flows and Universality in Classical Multifield Cosmological Models. Before I will ask Mirela to shortly introduce us with today's lecture, I would like to thank again to Calin for accepting our invitation to give a talk. To thank to our colleague from CERN, Marko Simonovic, who proposed this idea, and to thank Mirela, Maria Dimitrijevic from Belgrade, Ioannis Rizos, who are with me, are members of the organizing committee, and to Dr. Milan Milošević, who helps us in the technical stuff about that. So I would ask now Mirela to give a short introduction about Calin and his work, and then we will start with Calin's talk. So Mirela, it's your work.
Hello, everyone. As I know, Calin doesn't really like to be given a big introduction, so it's good that I will be short. Calin Lazaroiu is a Romanian physicist, but he has spent most of his career so far abroad. He has a PhD in physics from Columbia University in the USA and various postdocs in the West, such as in Stony Brook, Wisconsin, Madison, Princeton, and Humboldt University. He was a lecturer for 6 years in Trinity College Dublin and a senior scientist for 7 years in Institute for Basic Science in South Korea. Now he's back in Romania for a while, being a senior scientist in the Horia Hlubei National Institute for Physics in Bucharest-Magurele. Most of Calin's research is focused on geometric aspects of string theory. Okay, so Calin, you may have the floor now.
Okay, thank you for the introduction and for the invitation. So this talk is about classical multifield cosmological models. So even though I will use language that's somehow inspired by Wilson's theory of critical phenomena, which concerns mostly quantum aspects, this will all be applied in some sort of toy way to classical dynamics of cosmological models, so to a classical dynamical systems. So such ideas have been used before in the mathematical study of dynamical systems. They go under the name of dynamical RG flow. So, but the application and somehow it's different from what other people have tried. Okay, and they were never used in this cosmological context, as far as I know. So, this is the scheme of the talk. So what are these multifield cosmological models? So they are cosmological models with more than one inflaton. Okay, they are somehow the natural thing that you can consider where you have more than one inflaton. So let me just define them mathematically. So I'm going to start with the notion of a scalar triple, which consists of 3 pieces. A manifold, which I take to be connected and without boundary, endowed with a Riemannian metric. Okay, so this Riemannian manifold we call the scalar manifold. So 1 piece, 2 piece, and the 3rd piece is going to be a smooth real values function defined on this Riemannian map. Okay, and I'm going to make some assumptions which are physically justified. The first one is that this Riemannian manifold, this scalar manifold, is complete. This will ensure conservation of energy in my models. And the second, that phi is strictly bigger than 0 now. I can take it to be bigger or equal than 0, but that introduces some mathematical discussion that I want to avoid, some technical complication. So I will take it to be strictly bigger than 0. Okay, so if I give you this datum, a scalar triple, then I can associate to it a cosmological model. This is just by considering the action of Einstein-Hilbert gravity on R4, on a space with topology, space-time with topology R4, to which I add a kinetic term for the scalar fields and the potential term for the scalar fields. The potential term is governed by this scalar potential the kinetic term has the canonical form. So here I've written this section in a way that's completely geometric, completely coordinate free, and moreover, in a way that applies to any topology of the scalar manifold. So this M plays the role of the target space for the scalar fields. If you write this in local coordinates, then you will see that this term, this kinetic term for the scalar fields, is just a standard nonlinear sigma model action, to which you added some scalar potential. And then this is just the Einstein-Hilbert term. So here M is the reduced Planck mass, and later on I will use a rescaling of the reduced Planck mass, which I call the rescaled Planck mass. So I rescale the reduced Planck mass by square root of 2 over 3. This is just to simplify some formulas. And little g here is, of course, the metric on space-time on R4. So to obtain cosmology, you play the usual trick. You take G to describe a simply connected and spatially flat Friedmann, Lemaitre, Robinson-Walker universe. So you take it to be of this form. My conventions are that the signature is 3,1, so it's mostly plus signature. You denote the first coordinate with t. This will be the cosmological time. The rest are x1, x2, x3. And you further take phi, this collection of scalar fields, to depend only on the cosmological time. Okay, so that's what we usually do. You define the Hubble parameter as usual. So this is this conformal scale factor A of t of the FLRW universe. So the Hubble constant is the logarithmic derivative of A of t. It's not really a constant, it's a Hubble parameter, so it's a function of t. And when this Hubble parameter is bigger than 0, by a simple computation, you can show that the equations of motion from this section with these assumptions are equivalent to the cosmological equation. Okay, so they reduce to a single equation, which is written here in a coordinate-independent form. So I'm not choosing coordinates on this scalar manifold M. So this is now an equation for curves inside M, because phi depends only on t, and phi was valued in the scalar manifold M. It becomes a curve, a map from some interval in the real axis, valued in this Riemannian manifold M. And here you have the covariant derivative of this scalar field metric G, which specifies the kinetic terms of the scalar fields. Here you have the norm induced by G. That's the square norm of the vector tangent to phi at cosmological time t. Here you have, of course, the scalar potential term. This is 3 times the Hubble function. Okay, here you have the gradient of this scalar potential phi, which was a function defined on M with respect to the scalar field metric G. And this is the equation. Okay, so you reduce everything to the cosmological equation together with the condition that the Hubble constant is given by this expression as a functional of phi and phi dot. So I wrote here this expression in terms of a function defined on the tangent bundle of M, because phi dot really depends on t, so it's a tangent vector at the point phi of t to the scalar manifold M. So it's an element of the tangent bundle to M. And on the tangent bundle to M, you have this function, which I call the rescaled Hubble function, because I took out some 1 over 3M naught from it, for elegance. Okay, and pi in this expression is the bundle projection of the tangent bundle to M. Okay. So here you can see one reason why I took the scalar potential to be strictly positive is because I want this rescaled Hubble function to be smooth on the entire tangent bundle. If I allow some points in M where the scalar potential vanishes, then this would be continuous on the tangent bundle and smooth only on the slit tangent bundle, which is defined as the complement of the zero section inside the tangent bundle. So that's a kind of technical issue that I want to avoid. You can deal with it quite easily, but it complicates discussion. Okay, so that's why I took phi to be strictly positive. Okay, good. So now the solution curves of this cosmological equation, which is a second order ordinary differential equation formulated in coordinate invariant form, so it's a geometric ODE, are called cosmological curves. And of course, you have the usual theory of ODEs, so you are going to be mostly interested in the maximal solutions. In general, the maximal solutions are not defined on the whole real interval, okay, on the whole real axis, but just on some interval inside the real axis, which can be open or semi-closed or closed, but it will be non-degenerate in the sense that it's not reduced to a point. So the solutions are called cosmological curves. Now you can show that this cosmological equation defines an autonomous and dissipative geometric dynamical systems on the tangent bundle to M. So a dynamical system is just a manifold together with a vector field, and you understand the vector field as specifying a differential equation. Okay, so the differential equation being the equation for the integral curves of the vector field. But here it's a second order ODE, which is formulated in a manifestly coordinate independent manner. So you want to formulate it as a first order ODE by calling phi dot as a new unknown function. And that's a bit subtle to do geometrically, but it's well understood since Chern in the 1940s, early 1950s, how to do that. Okay. You do this using the theory of semi-sprays. So the corresponding dynamical system on the tangent bundle through this trick is defined by a vector field, which is a so-called second order vector field or semi-spray. So it's not an arbitrary vector field, and that encodes the geometric character of the initial second order ODE. But that's technical. And then, of course, if you have a dynamical system, the integral curves define a flow. This is an autonomous dynamical system in the sense that none of the questions depends explicitly on T. They depend on T only through phi or phi dot. So this flow will be defined on R cross Tm, or some domain of R cross Tm, and it's called the cosmological flow. So the cosmological flow is not necessarily complete. So it's not defined on all of R cross Tm because this semi-spray that comes from here is not complete in general. If M were compact, then you might naively hope that the flow would be complete, but that's still not true because the tangent bundle to M is never compact. Okay? So you have no assurance that this flow will be complete. And to have some kind of completeness result, you need to impose some pretty strong conditions on scalar potential. So in general, the flow is not complete. It's not defined on all of R cross Tm. Good. So this is the setting. So you can see from here that it's going to be a pretty complicated task to understand the cosmological curves. So you want to, if you want to study multi-field cosmological models, in principle, nobody tells you what is this scalar manifold. This scalar manifolds can be very high dimensional. You can have dimension 500. And there are such models in string theory which produce 500 moduli in the vector multiple moduli space and whatnot. It can have very complicated topology. Okay. This function phi can be quite complicated, especially since you typically want to break supersymmetry. You don't just start with something like a special Calin manifold or a Calin manifold, but you want to break supersymmetry, which will induce quantum corrections, which will modify the metric and the potential. So all of this data can be horrendously complicated. And to solve this in general, to say in general what this dynamic is not such an easy task. So there are some general results that you can prove, but they're not that rich. In particular, because in almost every application imaginable, the scalar manifold has to be non-compact. And a non-compact manifold can have very complicated behavior towards infinity. So one way to study it is to consider some sort of compactification of it, but there's no unique way to compactify. One way to compactify any differential manifold is Freudenthal or end compactification, which we'll use later. But you can have others, and the compactification that you want depends on the type of potential that you have and type of problem that you want to address, and so on and so forth. So things become very, very complicated. So it's not going to be a simple task to understand the dynamics of these models in any detail. So what are we to do? Well, one way to deal with this kind of complicated problem goes back to Wilson, namely to use a symmetry that typically exists in any type of system that has some sort of spatial or temporal extent, namely the scaling symmetry, and exploit that to the maximum. You use it in order to devise some kind of scale expansion and then classify the models according to the first terms of these scale expansions into universality classes and try to extract the essential features that survive in the limits of the scale expansion, short scale and large scale, the so-called ultraviolet and infrared limits. So let's try to apply this kind of insight into this system. That's the basic idea. Let's try to use Wilsonian ideas to try to extract the essential features of these horrendously complicated models at the classical level. So that's the idea. So the results will be as follows. First, we will introduce a dynamical RG flow for this system. So it's completely classical, nothing quantum. So it's a toy version of what Wilson did, which relates the UV and IR limits, ultraviolet and or short time scale, and infrared or long time scale limits. The two limits will correspond to fast and slow variation of the cosmological curves, or if you want, in the case when m is Rn, they will be via Fourier transform high and low frequency modes of phi of t of this curve. We'll consider the corresponding scale expansions and the corresponding UV and IR limits. These expansions are new, as far as I know. They are never studied for multifield models. We will show that leading approximants of the two expansions recover respectively the geodesic flow of the scalar manifold and the certain reparameterization of the gradient flow of a function called the effective classical potential of the model on the scalar manifold. So this classical effective potential is given by this very simple expression, is m naught, the rescaled Planck mass, square root of 2 phi. If this were a quantum model, of course, it would be something much more complicated, but here it's just an exact simple expression. And using these expansions, we will define the ultraviolet and IR cosmological universality classes, which allow for natural classification multifield models. And we'll show that the infrared cosmological universality classes will actually depend only on the conformal equivalence class of the scalar triple. So the equivalence class and the conformal transformation of the underlying manifold, the Riemannian manifold Mg, which preserve the scalar potential V. So this is similar to conformal invariance at infrared fixed points in Wilsonian theory. And then we have some applications. We studied a very large class of two-field models. First, we can show that two-field models whose scalar field metric has constant Gaussian curvature are infrared universal in the precise sense of Wilson, in the sense that it suffices to study such models in order to study all infrared universality classes of all two-field models, no matter how complicated this two-dimensional scalar manifold is. And the non-compact Riemann surface can be extremely complicated topologically. It's completely understood how, but for example, the space of Freudenthal lens can be very complicated, can be a Cantor space. Okay, so they are much harder to classify and much harder to describe than compact Riemann surfaces. Okay, and we'll study the infrared phases in the universality classes of such two-field models with certain conditions, the tameness conditions, which are actually pretty weak. And we can characterize all of them explicitly in the sense that we find the infrared approximants of cosmological curves explicitly. We have explicit expressions for those curves in terms of special functions. One can show that the infrared phases for such two-field models arising from non-planar ends or non-plane ends, which are type of Freudenthal lens that exist there, are qualitatively different from those of models based on the Poincare disk. So it is completely untrue that it's enough to study the Poincare disk, to the disappointment of some people. The phases associated to Freudenthal lens of the scalar manifold have exotic behavior different from that of hyperbolic dynamical systems. We can show, we can compare the first order IR approximation for such models with numerical studies, and we find through such comparison that cusp ends of hyperbolic surfaces appear in this uniformization result, are particularly interesting, and they lead to highly complex, fast-turn cosmological curves that are not well approximated by the first order of the IR expansion. So this is a summary of some results. Okay, so how do we do all of this? So first of all, we notice that there's some universal symmetry that all of these extremely general and complicated models have. That's Wilson's main idea. There's always some scaling symmetry. In fact, in this situation, there are two adiosymmetries, one of which will deserve the name of RG symmetry. So first of all, let me introduce a scale transform of a curve. So I take a curve in this scalar manifold M, defined with some interval. You can rescale the variable, the time variable, the only scale for this curve, by some positive parameter epsilon. That changes the defining interval. So you take t into t mod epsilon, you take the defining interval into epsilon mod I, so that t belonging to epsilon I. If T belongs to epsilon I, then T mod epsilon continues to belong to I, and all these formulas make sense. So that's the epsilon scale transform of a curve. Okay. So with this definition, it's very easy to check that the cosmological equation, this equation, is always invariant under two types of transformations. Under parameter homotopes, which consist of rescaling the scalar field metric, the scalar potential, and the mass by the square root of the scaling parameter, and scale similarities, which consist of these epsilon scale transforms, together with rescaling the potential by 1 over epsilon square. Okay? And a certain combination, I don't have time to explain here how you choose this combination, but it's explained in the paper, is called RG similarity. So it's a composition of the parameter homotopy, the first symmetry, at parameter epsilon square, lambda equal to epsilon square, with the scale similarity at parameter epsilon, which results in these transformations, this scale transformation of the curve, and these rescalings of the parameters of the model. So notice that the scalar potential remains unchanged. And this is, in fact, one criterion by which you can identify which combination of the symmetries deserves the name of RG similarity. Good. So the RG transformations will be that part of RG similarity which doesn't involve the scale transformation on the cosmological curve. So that's the transformations on the parameters that you see here. So you can take this as a definition. Okay. And it turns out, if you think about it, that these transformations play a role similar to that of RG flow transformations in critical phenomena, in the theory of critical phenomena. So the main result after some study is that the RG flow of this of the model parameterized by some value of the rescaled Planck mass and the given scalar triple interpolates between the geodesic flow of the underlying scalar manifold, which is recovered in the ultraviolet limit, which corresponds to epsilon goes to infinity, because T mod epsilon goes to 0 when epsilon goes to infinity. That's a fast oscillation or short time scale. And at the other end, a reparameterization of the gradient flow of the classical effective potential m naught square root of 2 phi, which is recovered in the infrared limit epsilon goes to 0, which corresponds to slow variation of these curves. Okay. So now there's some mathematical mumbo jumbo. So essentially you can introduce a plane inside the space of symmetric covariant to tensor tensored with R. So R parameterizes this escape Planck mass. And this line that I choose inside this space of symmetric to tensor parameterizes metrics up to a rescaling by a possibly negative number. And if you want to parameterize metrics themselves, you need to fix a number, to take the number to be positive. So you need to choose a half line there. So together, these things define some sort of cone, this R plus plus L plus. So it's some sort of way of talking about how M and G for a fixed reference metric G, when you just rescale G, can be parameterized. And the cosmological RG action on this cone is the action here, okay, where you leave phi unchanged, so it's not part of the picture. So inside of this cone, you can actually describe this action through a flow. So the action is just by scalings with powers of epsilon, so you just need the corresponding Euler vector field. And if you choose some reference metric, you can just view this as a cone, R plus cross R plus, with parameters W1 and W2, on which this RG transformation acts by rescaling W1 with epsilon and W2 with epsilon square. So the Euler vector field is given here. And if you do this change of parameter, epsilon is e to the lambda, you find that the RG flow identifies with these transformations. Okay? And with this reparameterization, the limit lambda goes to infinity recovers the UV limit, and epsilon goes to the UV limit, and lambda goes to minus infinity, corresponds to the ER limit. And these are the fixed points of the RG flow on the one-point compactification of the homotopy cone, which is how I call this cone, which are the apex of the cone and the point at infinity. So here is a picture. This is the kind of picture that you see in books on critical phenomena, right? So that's exactly the same thing, but now in a classical dynamical system. These are the integral curves of the RG flow on this homotopy cone. And here I've compactified because I want to show you the ultraviolet fixed point, which here corresponds to the point at infinity. I've compactified it, and I use the stereographic projection to represent a part of the Riemann sphere. So you can also present it like this. Okay? So the RG flow proceeds from the ultraviolet fixed point, to the infrared fixed point. Okay. So now, how do you actually express something useful? So this, until now, this is pretty much abstract mumbo jumbo. So yes, you have the scaling symmetries, very nice. This is a pretty simple thing because this is not a quantum system, it's a classical system, but what is this good for? Well, of course, you have to do scale expansions. So to understand the scale expansions, you want to consider this rescaled cosmological curve, this phi epsilon here, and see what equation it satisfies. So it's very easy to see that the initial cosmological equation is equivalent to this equation for this scale transformed curve. So you get some powers of epsilon appeared in various places. And you can divide this equation by epsilon square, and you can also write it like that. So if you write it like that, after dividing by epsilon square, you see that it's equivalent to the cosmological equation, but for a different scalar potential, namely a scalar potential which is equal to the initial scalar potential divided by epsilon square. In other words, phi satisfies the cosmological equation of the scalar triple mg phi if and only if its scale transformed by epsilon, phi epsilon, satisfies the cosmological equation of the scalar triple mg phi mod epsilon square. So the ultraviolet limit, epsilon goes to infinity, amounts to taking the overall scale of the potential to 0, while the infrared limit amounts to taking the overall scale of the potential to infinity, which is as you would expect, because the scalar potential gives you an energy scale. So if your motion is slow, the kinetic energy of the motion is slow, so it's much slower than phi, so phi appears large for you if your characteristic energy is small, while if your characteristic energy is large, if you move very fast, then phi appears small to you. So that's exactly what happens. So now you can do scale expansions. Because this is scale curve satisfies these equations, okay, where you have an explicit dependent on epsilon. So you can look for solutions of these equations expanded in powers of epsilon or 1 over epsilon. So these are the two scale expansions. So when epsilon is very large, you can expand phi epsilon in powers of 1 over epsilon square, it turns out. You can identify the types of powers appearing in the expansion just by looking at the form of the coefficients of the equation, what powers multiply various coefficients. And then you find that if you scale back to phi, that's the same as saying that you are taking the initial cosmological equation and you expand it into negative powers of phi, which is natural because the UV limit corresponds to taking phi to be small. So that's the same as saying that you just start with the initial cosmological equation without any scale transform. You take the reduced Hubble function, which is written here. You expand the square root because phi is taken to be small. You expand into powers of phi over normal u square. And then you seek solutions of the initial cosmological equation expanded in powers of phi. And the infrared expansion, you can play a similar game. When epsilon is much smaller than 1, you expand phi epsilon this time in positive powers of epsilon rather than epsilon square. That's equivalent to taking the initial equation, the untransformed function phi t, and expanding it into powers of 1 over square root of 2 phi. So in other words, you treat phi as large, as I said here. You expand the cosmological equation as written here, and then you seek solutions expanding the powers of 1 over square root of 2 phi. So these are the two scale expansions, the UV expansion and the IR expansion. It's a pretty natural and elementary thing to do. Okay? So of course, if you write down these expansions, you try to understand their terms, it's going to get really complicated. And I have a paper coming out on that. Because, of course, you want to do it geometrically, in coordinate-independent manner. This is a manifold with a complicated topology. You have to use exponential map, and so on and so forth. So, of course, the expansion is quite messy. And to arrange it nicely, it takes a bit of thinking, but it can be done. However, the first few terms are not too hard to understand. So if you look at the IR expansion, you see that the small expansion parameter, 1 over square root of 2 phi, multiplies the first term. As a result, you have a phenomenon that's well known in asymptotic analysis of perturbed ODEs. Namely, you have a drop of order of your ODE from 2 to 1 in the approximation, which is why the first order approximation is described by solutions of first order ODE. And that's what's going to happen in the first order, for the first order Weyl approximant that we'll see in a moment. In the UV, this doesn't happen. In the UV, it's there's no drop of order. Okay. In particular, this means by an old result of Poincaré that you cannot expect the IR expansion to ever be absolutely convergent unless you do some modification. So this naive IR expansion will always be at most asymptotic. Okay. So the leading IR approximant, well, in this case, you just expand to first order in 1 over square root of 2 phi, and it's easy to see by computation that the expanded equation for this first order approximant amounts to the gradient flow equation, where phi IR is the first order approximant in the IR expansion. But you find by computation that it's a gradient flow equation not of V, but of this effective scalar potential, which was defined as m naught square root of 2 phi. So this is the V that appears. That's just from a stupid computation. So you find that this is this gradient flow equation of the effective classical scalar potential describes the first order approximant in the IR expansion. And of course, you have to put the corresponding initial conditions, and there's some discussion here. If you want to describe this drop of order that I mentioned here, you can describe it mathematically by considering the gradient flow shell of this effective scalar potential, which is just the graph of the gradient of V inside the tangent bundle. And the precise mathematical result is that the cosmological flow of the model is approximated to first order of the IR expansion by this infrared approximant of the flow, which is defined on a domain which is the domain of definition of the gradient flow of this effective scalar triple. So the scalar triple in which you replaced phi by the effective scalar potential V, which was m naught square root of 2 phi, lifted through this gradient vector field to the gradient flow shell of M, which was a closed sum manifold of Tm. So this is mathematically precise and elegant way to formulate what is the first order approximant of the whole cosmological flow. First order infrared approximant. So here you can discuss how good the approximation is. So one of the results is that the approximation is the best for a certain class of curves called infrared optimal curves. These are the curves whose orbits meet the gradient flow shell of the effective scalar triple. So by the orbit, I mean the lift of phi to the tangent bundle. So you look at phi and phi dot, which is a point in the tangent bundle, and if that meets the gradient flow shell, which is a closed sum manifold of the tangent bundle, then you say that the curve is infrared optimal. And you can show that these, for some time intervals around the time at which the times at which they meet the gradient flow shell, are approximated, are the best, are the curves that are best approximated to first order in time by this infrared approximant. Okay, and you can do various other things, and you can find them in the paper, such as work out the consistency conditions of linear approximation. You can show that the approximation implies the first roll condition. However, it is much more restrictive than slow roll. So imposing slow roll is not the same as imposing IR, but imposing IR implies in particular that you impose slow roll, but you impose many other things. Okay. So, as announced, you can show now quite easily that you have a conformal invariance property in the infrared approximation. So, namely, this very simple fact, which follows from simple computation, namely that the gradient flow of a scalar potential V defined on a Riemannian manifold is invariant under Weyl rescalings of the metric of that manifold up to reparameterization of the gradient flow curves. This is just a simple computation. It's, in fact, of course, well known to people who study gradient flows. So now a definition, two scalar triples are called conformally equivalent if there exists a smooth conformal diffeomorphism, or conformal diffeomorphism is a diffeomorphism of the underlying manifolds such that the pullback of the metric of the second manifold through F is proportional to G1 via a function which is everywhere positive. Okay, so they are called conformally equivalent scalar triples if you have a smooth conformal diffeomorphism such that V1 and V2 are related through that conformal diffeomorphism. In this case, F is called the smooth conformal equivalence of the two triples, and the conformal automorphism of a triple is, of course, a conformal equivalence from the triple to itself. So you can generalize this previous proposition, which was about Weyl invariance under Weyl rescalings, to something slightly better, namely the gradient flows of conformally equivalent scalar triples are smoothly topological equivalent. This is slightly more general result. Okay, so with these preparations, you can define infrared universality classes. The idea is the same as usual, namely you want to identify the transformations which identify to describe the transformations which identify the infrared approximants, in this case the first order infrared approximants of two cosmological models, and identify through the corresponding equivalence relations. So here you find that the transformations which identify the IR limits are so-called gradient equivalences. So you say that two effective scalar triples are gradient equivalent if there is a diffeomorphism between the underlying manifolds, which relates the gradient vector field of one of the triples to a rescaling of the gradient vector field of second triple by some smooth positive function, omega. This defines an equivalence relation on all scalar triples, and you define a conformal. You define two classical cosmological models to be IR equivalent if the corresponding scalar triples are related by a gradient equivalence, and the equivalence relations of scalar triple of models of cosmological models under this binary relation are called infrared cosmological universality classes. So you have a precise mathematical description of IR universality classes. And there's a simple example of such a gradient equivalence, namely a conformal equivalence of scalar triples, which is what we had before. It's the statement that one invariance that you have in the infrared is invariance under conformal transformations of the triple. But you have more identifications in the infrared than just conformal equivalences. Okay, so this is a pretty weak equivalence relation, as you can see from here, if you think about it. So it allows for a pretty coarse classification of cosmological models. So if you just want to study the infrared universality classes of cosmological models, then you extract only those features which survive in this very slow motion of cosmological curves. And you can see why that is relevant, because this infrared limit means that you move at low energy, low when compared to, let's say, the Planck scale or whatever appears in cosmology, whatever are natural energies there. And as I said before, that implies slow roll. So that's exactly the kind of approximation you want to have. And moreover, of course, you can do a lot better. Here I'm just declining the first order because you can do higher orders of the scale expansions. So in principle, you can devise an approximation scheme by which you can compute all cosmological observables and interests order by order in the infrared scale expansion, which is the kind of thing that you would like, because you have no chance of ever solving such models explicitly, but you want to have a rough approximation of the scaling limits and then build systematic corrections on top of that. That's exactly what Wilson did in the theory of critical phenomena, and now we can do it in the classical theory of multifield models. That's the insight. Good, so let's look at an obvious application, namely to field models. So in that case, we have the well-known universality, well-known uniformization theorem of Poincaré, which says that the Weyl equivalence class of any Riemannian metric on a borderless connected surface, whether compact or non-compact, it doesn't matter, contains a unique complete metric called the uniformizing metric of G, whose Gaussian curvature is equal to -1, 0, or +1. So that's an extraordinarily general result. It applies to any Riemann surface which is connected and without boundary. In fact, there are versions which apply also for certain types of boundaries, for some or metrics which are way behind on boundaries, but that's not relevant here. Okay, the Riemann surface does not have to be compact, It can have an arbitrarily crazy space of Freudenthal ends. It's a totally general result. It's a fantastic result, by the way. So the generic case is a case of negative constant Gaussian curvature, also called the hyperbolic case. In the case when the uniformizing metric has negative Gaussian curvature, so equal to -1, you say that the original metric is hyperbolizable, and the uniformizing metric is called its hyperbolization. And then the cases when the Gaussian curvature of the uniformizing metric is +1 or 0 are exceptional. They can occur only for 7 topologies, which are completely classified, and I won't insist. You can find this in any book on the theory of Riemann surface. Okay. So using this result and using the fact that you have conformal invariance in the infrared, which means that the infrared universality classes don't feel this Weyl equivalence at all. You lost all the information in the Weyl scale factors when you went to this infrared limit. You have an obvious consequence of the Poincaré uniformization theorem, which says that up to curve-dependent increasing reparameterization, the R behavior of the cosmological flow of a two-field model with scalar triple sigma G phi. Sigma is the surface, target surface for the two scalar fields. Every scale plane mass of M naught is described by the gradient flow of the effective scalar triple sigma GV, where this Roman G is a uniformizing metric of G. This is where you throw away that Weyl factor. And V is the classical effective scalar potential of the model. So that's the previous result about gradient flows describing the IR limit. So this result is very powerful, right? So it tells you that in the infrared, you've reduced all that complicated stuff with something much simpler. First of all, you replaced that arbitrary matrix G on this arbitrarily crazy surface sigma by the uniformizing metric, a metric of constant scalar curvature. And you replaced this phi by this effective potential. And instead of studying this cosmological equation, which in general is impossible to solve, except numerically, you are reduced to studying a much simpler equation, which is now first order rather than second order, as the cosmological equation was, namely the gradient flow equation of this effective potential on this surface, which is now endowed with a metric of constant curvature. And in the generic case, this metric is, of course, hyperbolic, because that's the generic case. And everybody should know by now that two-field models whose complete scalar manifold metric has constant negative curvature are called generalized two-field alpha attractor models. The simplest one of these were introduced by Rushd, Linde, and Kalosh. They are the ones where sigma has trivial topology, so it's just a Poincaré disk, right? The unit disk endowed with Poincaré metric. But of course, in general, you can have a hyperbolic sigma of very complicated topology, okay, because it's non-compact, so you can have a very complicated space of ends. And if you allow for arbitrary topology, then you call them generalized two-field alpha attractor models. So the corollary from this is, in particular, so in the corollary hyperbolic case, is that generalized two-field alpha attractor models are infrared universal among two-field cosmological models with hyperbolizable target manifold. So this gives a conceptual reason to single out generalized two-field alpha attractor models for special study. So here I should briefly mention that there were claims, vague claims about universality of alpha attractors, by which people invariably mean just a Poincaré disk, so trivial topology, but they never really explained in what sense they use the word universality. This gives you a theorem. This is a theorem based on what I did. This is completely clean, okay? Of course, the hard result behind is not what I did. The really hard result is Poincaré's uniformization theorem. So it's a very precise result which tells you that generalized two-field alpha attractor models, so you have to allow all topologies which can support complete hyperbolic metrics, okay, which is not what they initially claimed, are infrared universal in this very precise Wilsonian sense, which is the correct sense, sense of the word universality in physics, yes, among all two-field cosmological models whose target manifold is hyperbolizable, which are not all the models, but they are the generic models. The non-hyperbolizable surfaces are just of 7 types. So you have said to study 7 types of scalar manifold metrics, topologies and metrics, plus all this infinite class of hyperbolizable models, which are all described by two-field alpha attractor models in the infrared limit. So that's the correct way to formulate what these people were trying to say. And I think this was completely not known before these papers. I don't think that they ever tried to define precisely what they mean by universality of alpha attractors. They have all these big words in the title, but there's never really anything more than some very vague statement, which is in fact incorrect. I mean, it's not, because they are not truly universal. You have these other cases. And also you have to consider all topologies that admit complete hyperbolic matrix, not just the Poincare disk. Good. So now as an application, you can put some technical conditions. You can consider tame hyperbolizable two-field models. So these are two-field models which satisfy 3 conditions. The first one is that the fundamental group is finitely generated. So this rules out those crazy cases when you have an infinite space of n's, such as, for example, a Cantor space. So if you require that the fundamental group of this non-compact surface sigma is finitely generated, so this is just for the non-compact cases, then the space of n's is finite. And you can present sigma as a compact Riemann surface minus a finite number of points. So just take out, you just perform a number of punctures, finite number of punctures on a Riemann surface. So that's a massive simplification topologically. Okay, the second condition is that the scalar potential is globally well behaved, by which I mean that it admits a smooth extension to sigma hat, where sigma hat is a Freudenthal compactification. Is this compact Riemann surface from which you took out a finite number of points, the Freudenthal compactification of sigma. And you further require that this smooth extension is strictly positive on sigma. In principle, it's determined by continuity, but in principle, it could be 0 at some of the ends. Because by continuity, the condition that phi was strictly bigger than 0 becomes phi hat bigger or equal than 0, and I want to rule that out. So I require that phi hat is strictly bigger than 0, again, for technical reasons. Okay? And finally, you require that the extended potential is a Morse function of sigma. This is a strong requirement. That means that it doesn't have non-isolated critical points. Every critical point has positive Hessian, and therefore it's isolated. And that you require for the extended potential on this compact Riemann surface sigma hat. And because sigma hat is compact, that means that phi hat has only a finite number of critical points. So among these critical points of phi hat, you have the critical points of phi, but also some critical points of phi hat, which correspond to some of the ends, the Freudenthal ends of sigma, those punctures that you add to go from sigma to this compact Riemann surface sigma hat. So two-field cosmological models whose scalar triple is tame, in the sense it satisfies these 3 conditions, is called the tame two-field cosmological model. Okay? So notice that this is a very large class of cosmological models, because sigma hat can be any compact Riemann surface, so it can have arbitrary genus. Okay? And you can take out any finite number of points to produce the ends of sigma. And you can have a scalar potential which is very general, as long as it has its extension to sigma hat. It has an extension to sigma hat which is Morse, which is smooth, strictly positive, and Morse. Okay, and of course it's a classical theorem in Morse theory that the space of Morse functions is dense in the space of smooth functions on a manifold. So by small perturbation, you can make any smooth function to be Morse. Okay, so it's still a pretty large class of models. Okay, good. So now, of course, some of the critical points of this extended scalar potential are just the critical points of phi, which I call the interior critical points, because sigma is somehow the interior, so to speak, of sigma hat. It's sigma hat minus finite number of points. Then you have critical ends, those punctures, right, that you added, those ends at which are critical points for the extended potential, and you have non-critical ends, those ends at which the extended potential does have a critical point. And you have to consider all of them, and you can study them. And what helps you is exactly this result. by this result, it suffices to consider hyperbolic metric on these surfaces. Okay. And the theory of geometrically finite hyperbolic surfaces, which are those hyperbolic surfaces whose fundamental group is finitely generated, is very well studied. It's a very classical subject. And by this theory, you know the form of the hyperbolic metric in a vicinity, in a canonical vicinity of each end. So you know the local form of the metric for each of these ends that you added in order to go to a complex surface heap. Okay, and it's given here. There are some exponentials, hyperbolic sinuses, cosinuses, etc. Okay, so in these coordinates, the end corresponds to whatever local coordinate r I have here going to infinity. There's a rotational invariance around the end, an local U1 isometry around the end in this matrix. And you can look at the asymptotic form of this matrix close to the end, and they are characterized, are given here, they are characterized by two constants. One is a sign, +1 or -1, and the other is one of 4 values. There are 4 types of ends: plane end, horn end, funnel end, and cusp end. The flaring ends are those for which epsilon is +1. These are the plane, horn, or funnel end. And the remaining end is a cusp end for which epsilon is -1. So this is some well-known result from the theory of hyperbolic, geometrically finite hyperbolic surface. Okay, so this is the fundamental result that you use. This tells you that if you look close to an end, the form of the metric is known. Of course, the form of a metric is local form of the metric. The local form of the metric is also known close to any point of sigma in the interior, so far from the ends. This just by Poincare uniformization. There's a small enough neighborhood of an interior point, which is isometric to a piece of the Poincare disk. And of course, we also study those in a paper. Okay, but the important things are the ends, because these are somehow at infinite distance in this scalar field space. And these are usually not so well understood. Okay. So, and these are the most interesting pieces. So there are now some convenient coordinates that you can choose there. It's pretty technical, and some quantities that characterize the expansion, Taylor expansion of this extended effective potential around each end. And I will jump over this because it's technical and a bit boring. And using these expansions, because that's the only thing that matters, you can completely determine the asymptotic form of the first order IR approximant near each end. Simply because you can study the gradient flow near the end in this quadratic approximation, Taylor approximation for the extended scalar potential expanded around the end. And you can actually solve it explicitly. And you can find that the gradient flow equations can be solved explicitly in terms of this incomplete gamma function of order 2, which is given here, just a combination of exponentials and monomials. And they have this form. Okay, so this is for non-critical ends, those ends which are not critical points of the extended scalar potential. And here is how they look like for plane, horn, funnel, and cusp ends. Then you can look and compare them with infrared optimal cosmological curves near non-critical ends. These are computed numerically, and study how good this first order approximation is, R approximation is. Then you can do the same thing for critical ends. Again, you find an explicit solution in terms of this gamma function and these coefficients which give you the asymptotic form of the metric near each end, this epsilon E and C to the E. You find that these gradient flow orbits depend only on these critical quantities, which play a role similar to the critical exponents in Wilson's theory of critical phenomena. And again, you can study them. We have a lot of mathematical propositions about them because the graphs don't tell you the full story, so you have to prove some theorems. But this is how they look like. Then these are numerical trajectories with which you can compare. Okay, numerical solutions of the exact cosmological equation. And so these are for various ends: plane end, horn end, critical plane end, critical horn end, critical funnel end, critical cusp end. And it's very interesting what happens at the cusp ends, because here you have trajectories which seem to densely fill a certain domain close to the end. So the ends are at the origin in these special coordinates that I chose. And here I show you some trajectories near a cusp end, so you see how they behave. It's pretty crazy. So you see that they, in particular, end up rotating fast and then oscillating fast and so on. So they have fast turn. Okay, so it's a very easy way to obtain fast turn if you go to a close to a cusp end of such a model. Okay, and that's where I will stop. So you can see everything very explicitly in this tame two-field models. Okay, so that's it.
Okay, thank you. Does anyone have questions for Calin?
I would have something like two questions. First, Calin, concerning the motivation for the supersymmetric, can you give any comment about the current and future results of trying to find the signals of supersymmetry about LHC?
Okay, so there's no supersymmetry in this. So this is very, very general. I'm not assuming any supersymmetry. So everything I said here is for models with an arbitrary scalar potential. So the supersymmetric models appear by assuming that the scalar manifold metric is scalar. Okay, and in fact, Kähler-Hodge, you need it not only to be a Kähler metric, but also you need the Kähler form of that metric to be an integral form, in the sense that it's integral over cycles in this Kähler manifold M. Over two cycles are integral. And also by assuming that this phi is given by the form, for example, in n equal 1 supergravity. So it's the exponential, well, it's essentially the norm of the gradient of the superpotential minus 3 times the norm of the superpotential all squared. That's this norm of the gradient of W squared minus 3 norm of W squared, where W is a section of a holomorphic section of a line bundle defined on this, of a holomorphic line bundle defined on M. So Mg has to be Kähler in n equal 1 supergravity, which is M is a complex manifold, G is a Kähler metric, and if a Kähler-Hodge, so a Kähler metric whose Kähler form has integral periods, and phi has to come from a superpotential, from a holomorphic section of a holomorphic line bundle defined on M through that formula. Okay, so that's much more restrictive than what I did. Okay, so if you want to embed these cosmological models in n equal 1 supergravity, and I do this with Lilia, and it's of course a long story. So for two-field models, it's of course rather easy because a non-compact Riemann surface. Okay, so if you put a any complex structure on a non-compact Riemann surface, that's a Stein manifold, which means in particular that any holomorphic line bundle on, and moreover, every holomorphic vector bundle on a Riemann surface or a non-compact Riemann surface is holomorphically trivial. That's a result of Forster, mathematician. So in that case, this holomorphic line bundle, which supports the superpotential in n equal 1 supergravity, is holomorphically trivial. Every Hermitian metric in 2 dimensions, in 2 real dimensions is, or 1 complex dimension if you want, is scalar. Okay, so to make the long story short, for Riemann surfaces, it's very easy to characterize, to embed them in supergravity. Okay, if you want to characterize those scalar potentials which can be embedded in supergravity. Okay, in particular, all these models which are hyperbolic can be embedded in n equal 1 supergravity if you take phi to come from a superpotential in that way. But of course, not every phi comes from that superpotential. Okay, so that's about embedding in supergravity. So that's n equal 1 supergravity. So that's one step above what I did. Everything I did here is not supersymmetric. So if you want to compare to LHC, you don't have any issue with supersymmetry. You just have to do some computation here and try to compare to the matter content that you see at LHC. But of course, the only way to do this in cosmology is to look at the early universe, to extract some cosmological predictions from this, okay, and really compare to what you see from cosmological observations. You don't have anything in the lab that could test such a cosmological models. I mean, all you know from the lab are the parameters of the standard model, and you can fit those to late stages much after the inflationary stage of the universe, and try to derive from there constraints on the inflationary stage, and then compare those constraints on the inflationary stage with the prediction of such a model. So it's a very indirect thing, but in any case, you don't. LHC only fixes the parameters of standard model that then get fit back to what happens much after inflation.
Yeah. Okay, so maybe it can be
any direct evidence from the LHC, even from the existence of a single inflaton. So we don't know for sure that an inflaton exists. We deduce this just because single field models seem to fit what we see in the early universe, like this small anisotropies of the CMB.
I want to just to connect somehow with LHC. In fact, it can be probably much better and much more precise formulated as that your approach does not have anything directly to the minimal supersymmetrical model, because minimal supersymmetric model is
this is
exactly
cosmology. Of course, it has nothing to do.
No, I mean,
this is cosmology. Of course, it has nothing to do with the LHC. It will be tested by cosmological observations, right?
No, but I'm not.
The CMB, whatever.
Let me stress here. None of these papers and nothing in these talks assumes supersymmetry. Okay, so these are non-supersymmetric models. There's no trace of supersymmetry here. This is just gravity coupled to scalar matter. But I have many scalar fields, and I studied this non-supersymmetric system. So there's no supersymmetry in this.
I wanted to understand it in the framework what we discussed just before your talk, when we discussed about supersymmetric, let's say supersymmetric cosmology.
That's different from what I'm discussing here. So
yeah. So Lilia was not apparently with us at this beginning.
Okay,
so,
sorry then. Sorry.
So I wanted to put it in a wider framework, Calin. Of course,
I haven't tried to connect this to anything like a realistic phenomenological model of supersymmetry breaking, anything like the MSSM, anything like this. So this is, I think, is far removed from this problem. So here I'm trying to address the much more basic problem of how to describe the dynamic of models with more than one inflaton. It's very hard to describe it in general.
Okay, so, two small sub questions, if I can.
Observations and speculate about what sort of supersymmetry you could have and how that would look like. Let's say if you have it in string theory, you go back to supergravity, you break it down all the way to something that might or might not be MSSM, and then try to go back to the LHC scale. It's such a long sequence of many things that you have to do, and I don't think that you can impose many constraints on such models from that. I mean, we are so far. In my opinion, we are decades away from being able to connect this sort of stuff to anything you see in lower energy cosmological observations, let alone.
Okay, you partially answered my first sub question. It was related to the can the current observational data make some distinctions between the model or models you develop and some other number of the models? So it is not possible at that level.
No,
and
not.
The last question is related to did you deal and are you going to work more on the primordial gravitational waves in the framework of you proposed to us, or you are doing not presented today?
No, I'm not. Actually, I haven't looked at that, and I'm not sure that I plan to look at that. Okay. I mean, my focus is mostly on understanding the dynamics of these multi-field models, because I think very little is known about it. But let me point out about your previous question. So at this point, we don't have any observation that could even distinguish between a one-field model and a two-field model. I mean, we have no evidence that we have more than one inflaton. Okay, we might have more. We might just have one, and in fact, strictly speaking, we don't even know if the inflaton exists. We have no direct measurement of something like inflaton. inflaton, any characteristic of an inflaton, we think that there should be at least one, you know, scalar field which is uncharged. But that's very indirect from cosmological, from matching early universe cosmological observations and tracing them back to what we think might have happened in the early universe. So we are very far from even knowing if we have two fields. So the motivation for this project is more theoretical, because only quantum model of gravity which doesn't somehow predict moduli. I mean, the only convincing models we have are in string theory. They tend to predict large numbers of scalar fields, and this is a fundamental conceptual problem: how you go from them to a one-field model. And for this, you'd have to understand in some detail the dynamics of multi-field models to understand what actually happens when you go to the infrared, that you end up eating most of those other scalar fields, and you end up with something like a one-field model or a model with a small number of fields. That's the kind of question, but it's theoretical. I think we are very far from testing this stuff to the level that you hope. Maybe a few decades.
Okay, thank you. Maybe there will be some other questions, so thanks again.
Okay, if there are no more questions, then thank you very much for the talk.
Okay.
And
yes.
Thank you, Calin. Calin, could you please stop sharing? I would just use 1 second to share something. Okay. So just a reminder for the people who are here. We will stop this online seminars and session, and our next activity will be assessment meeting and workshop in theoretical and mathematical high energy physics, which will be, as you can see, in Belgrade 1st to 4th of September. So everybody is welcome to join us. We will mostly work on site. Maybe there will be some opportunity for 1 or 2 talks outside, or we can put something online. This is still not very clear, because before that there will be a huge congress of the Balkan Physical Union with about 300 to 400 participants. So please follow our webpage, SEENET-MTP web portal, and we will inform you through the emails as for this talk. And in September, we will announce the continuation of our program further. So, Mirela, it's up to you to close today's session.
Okay, thank you everyone for participating. Thank you, Calin, for the talk, and see you next time.
Okay, bye-bye.
Bye-bye to everybody.
Bye-bye, Goran.
La revedere, Mihai.
Bye.